So for our first topic area for transit analysis, what we're going to be looking at are the types of transits associated with faults on power system circuits. And we're going to refer to this as an RL circuit analysis in a way, because the equivalent circuit that's kind of associated with this is going to be kind of a Thevenin equivalent, where we have a voltage source and we have resistance and we also have inductive reactance. And so before I get into this material, let's talk a little bit about what these waveforms might look like, because I'm not sure if you guys have ever seen snapshots of these before. But here's a recorded field waveform that was taken from a measurement device in the substation. And what we see is that before the fault occurs, what we observe is we've got this normal steady state fault current where the currents are somewhat balanced, not exactly because load's not always exactly balanced, but the phase currents are shown by the red, blue, and the green waveforms. The black waveform turns out to be the neutral current, which is the sum of the three currents. So anyway, before the fault occurs, you have somewhat balanced currents at a low level. I know the scale is kind of hard to see, but this is 500 amps, 1,000 amps, and 1,500 amps. And so what we have is we've got a zero to peak value for the current of a couple hundred amps. Remember, that's a peak value, so I have to divide by square root of 2 to get that in terms of RMS. And when the fault happens, this is obviously a single phase fault. What we see is we see this current going high. And what's interesting about this, if you're going to compare the initial first cycle of the fault current to the last cycle of the fault current, what you see is during the first cycle of the fault current, that value, that instantaneous value, is actually higher than what we'd have toward the end. In fact, what you could actually see on here, there's sort of a decaying DC offset where this whole waveform kind of gets shifted. In this case, it gets shifted up. But after a certain period of time, the fault gets cleared, and then we get back to the normal load current again. So anyway, what we're seeing in this case is we're seeing an actually recorded waveform. We have a fault that's lasting for about 6 cycles, which might be about the time it takes for like a station breaker to clear a fault. And what we see is that we have kind of like a symmetrical value toward the end, but at the very, very beginning, it's asymmetrical. It has a DC offset that's associated with it. Now, there's other types of faults that you guys have probably heard about. You can have line-to-line faults, you can have line-to-line ground faults, you can have three-phase faults. We're going to be just initially focused on looking at this very simple type of fault, which would be just a single line-to-ground fault. But if you were going to have two phases connected together, this is what you would have as far as the recorded waveform of the substation. What's kind of interesting about this is that these current waveforms are 180 degrees apart. And the reason you would have something like this, if you had three-phase, basically if you have a line-to-line type of fault, what you're creating is you're creating a loop current. The neutral for this is not very high. There's a little bit of neutral current associated with this, but basically you're creating a loop current where the two faulted phase currents are going to be off by 180 degrees. And then for a three-phase fault, which is probably more the scenario you initially did any sort of circuit calculations with when you started learning power systems, what we have for a three-phase fault is we have all three phases that are connected together. And in this case, what we're going to get is in steady state, we're going to get the same current magnitude per phase. You're just going to be off by plus or minus 120 degrees. Now, you do see when the fault first starts that there's a little bit of noise here at the very beginning. There's a little bit of DC offset which occurs on the three phases. But then after a while, what happens is this kind of goes into like a more of a steady state until the fault eventually gets cleared. So anyway, what we're going to be talking more about today is just some basic transit analysis for how we can get this fault current and how we can figure out how much DC offset are we going to have to this fault current. And where this becomes important, if we go back to this first slide, is basically what the circuit breaker is going to have to be able to handle is this peak value. All right, so we got to make sure that our circuit breaker is going to be sized and rated in such a way where we can handle what sometimes is referred to as the asymmetrical current component, where the symmetrical would be what you would calculate using kind of conventional phasor analysis. So the way I'm going to organize this material as far as the lectures is there's going to be part one, where what I'm going to do is go through this PowerPoint set. Primarily, I'm going to focus on the theory. This is also going to coincide with some material that I have in another PDF, some old class notes I'd actually written some text for before. And then what I'm going to do in a separate video is I'm going to go ahead and go through a worked example. This is more like some handwritten notes. It's just more convenient if I just switch over to a separate recorded video for this. And then there's going to be a third video on how we can actually construct the circuit in the PSCAD Transient modeling tool and actually run and get results that we're going to match up with what we get with the hand example. So let's take a look at how we can write some differential equations to solve this case. So we'll use a very basic model for the source. Basically, we'll use a Thevenin type of equivalent. And the Thevenin type equivalent is going to have a voltage behind a resistance and an inductance. And the assumption we'll start off with is that basically at some point what we're going to do is we're going to go ahead and close this switch, and what this is going to represent the initiation of fault. In this case, I'm not showing any pre-fault load. If you wanted to do that, we could put some resistance in there, and we can have some pre-fault load, and this would, something we could still solve. But let's start with something more basic than that. Let's just assume there's initially no load in the circuit, and then the fault's going to occur. And when I solve my differential equations, what I'm going to do is I'm going to go ahead and I'm going to be assuming that the switching action occurs at time equal to 0. And so the boundary conditions for this would be that right before the fault occurs, I have no current. So we say that I at 0 minus, right before the fault occurs, is equal to 0. And then right after that switch closes, we know that the current going through this inductor cannot change instantaneously. So what this means is that the current at 0 minus, right before the switch operates, is equal to the current right after the switch closes, which are both equal to 0. And if we want to simplify this, we basically say that the current at time equals 0 is equal to 0. So that's what we refer to as the boundary condition. This is a boundary condition due to the physics, to the fact that the current going through an inductor cannot change instantaneously. And when we talk about capacitors, voltage across the capacitor cannot change instantaneously either. Now, how do we model the fact that when that switch closes, we might actually have a different voltage at this source, because this is a sinusoidal source right here. And we've already said that we're going to assume the switching occurs at time equals 0. So you could actually have different source voltages when that fault occurs. Well, what we're going to do is we're going to model that source voltage by a magnitude, square root of 2 Vm. Vm is, you can think about that as a 0 to, I guess you can call that the RMS voltage, I guess, associated with that source. If I multiply by square root of 2, that gives me a 0 to peak value. And then I'm multiplying that by sine with an argument of omega t plus theta. And you could also work this out using the cosine. It's just more convenient in this case to use sine. And so basically at time equals 0, what we're going to have is we're going to have a certain phase associated with that source, which is going to give us what we call different points on wave. And so what would actually happen if I have a sinusoidal source? Maybe the fault occurs at a 0 crossing, maybe it occurs at a positive peak, maybe it occurs at a negative peak, maybe it occurs somewhere in between. I could change that voltage at which the fault occurs by changing that value for theta. So that's what we refer to as the point of wave angle. And so if I were going to write a loop equation for this, where the voltage is equal to the drop across the resistance and inductance once that switch closes, then for time greater than 0, I'm going to have L di dt plus Ri equals square root of 2 Vm times sine omega t plus theta. And I should probably write here, this is for time greater than or equal to 0. Now, when I talked about the form of solving these equations in lecture 1, I mentioned that we could think about the solution as having two parts. There's a steady state part and there's a transit part. The steady state part can be solved using phasor analysis. That would be the simplest way to do it. But the transit part, what we're actually going to do is we're actually going to have to solve a differential equation to get that transit part. But what we're going to do is we're going to superimpose both those parts together and apply the boundary conditions in order to get the total answer. So for doing phasor analysis, well, how would I get this particular current? Well, what I'm going to do is I'm just going to have a simple loop equation, but it's going to be a loop equation for a phasor-based circuit. And so what I'm going to do to get this steady state phasor, which is denoted by this tilde, is I'm going to take the RMS voltage magnitude at angle theta. I'm going to divide through by the impedance. The impedance is a complex number, R plus j omega L. The magnitude is given by square root of R squared plus omega L squared. It's going to have some angle phi that's going to be given by the arctangent of omega L over R. And I'm going to have a form for this current, which is going to be the source voltage RMS magnitude divided through by the magnitude of the impedance at angle of theta minus phi. So again, theta is the point of wave in the waveform that we're going to have when the fault occurs. Phi is going to be dependent on this ratio of omega L over R. We see this term quite a bit, this omega L over R. This is what we also refer to as the X to R ratio. And what I would expect for transmission systems, this X to R ratio would be pretty high, at least 10. For distribution though, for medium voltage and lower, this value is going to drop down. And so this value of X to R can actually change depending on where we're at in the circuit. So anyway, if we want to convert this back to the time domain, we could easily do this. We can take the magnitude, we can multiply by square root of 2 to get that back to 0 peak. And then where I have this theta minus phi, then I could basically substitute that to the argument of the sine term. And this is what we would have in the time domain, or I could plug this into MATLAB and I can actually get a plot of this. But this is just simply going to be a sinusoidal waveform. We're more interested though in looking at the form of the transit solution. And so what we need to do to get the transit part of this is we basically solve the differential equation, but with no forcing functions on this applied to the circuit. So basically on the right hand side of the equality, it's just simply equal to 0. And we're going to want to solve L di dt plus Ri is equal to 0. We want to find out what's the form of that current. And so if you were going to substitute wherever you see di dt, you substitute for s times I. If you have a second derivative, you substitute by s squared times I. What we're going to have is we're going to have in the Laplace domain Lsi plus Ri. And as far as the characteristic equation, what we're going to have is we're going to have SL plus R, and what we're going to want to do is we're going to find the roots of that to get the form of the solution. And so what this characteristic equation it's going to be is going to need solving is SL plus R is equal to 0, or I can divide both sides by L and I get this characteristic equation in the more common form of S plus R over L is equal to 0. And S in this case is minus R over L. So whenever you see a differential equation that has a single real root, then basically what this means is the solution is going to have the form of e to the st. If I plug in for minus R over L, this is e to the minus R over L over t times t. and then there's going to be a coefficient that we're going to need to determine A. All right. So this is the transit portion of the solution. What you see at time equals 0, this is equal to A. And as time goes to infinity, then this exponential term goes to 0. So what this represents is this represents what we call a decaying exponential or decaying transit. So it's going to start at some value and eventually it's going to disappear. So when we add both these together to get the total solution, we've got the steady state part, we've got the transit part. We just simply add these up together, and now what we need to do is we need to figure out, well, what's this value of A? So in order to get this, what we need to do is we need to apply the boundary condition. And the boundary condition, as we talked about at the very beginning, for the case of no load, is that this current at time 0 is equal to 0. And so if I set time equals 0 in this particular equation here, I get the square root of 2 Vm over r square root of r squared plus omega L squared times sine theta minus phi plus A is equal to 0, which means that A is shown right here. It's going to be the minus of this particular coefficient, this whole kind of complex term. So when I plug this in, what this does is this gives me a final solution for the current that has a sinusoidal part to it, and it has a decaying DC term on it, where you got kind of a complex expression right here for what the magnitude of this is going to be. Now, a lot of times what we're going to be concerned about is what's going to be the worst case. You know, how much DC offset could we actually get? But you can see this is going to be dependent on what this ratio of omega L over R is, and it's also going to depend on the point of wave in which the fault occurs. It depends on what theta is going to be. All right. So anyway, here's just a plot of what this is going to look like when you plug in for a 10 kV circuit. I've got a 10 kV circuit. If I've got a value of Z equal to 10 that corresponds to an X to R ratio of 10 as well, if I have the fault occurring when theta is equal to 0 degrees, you basically see what we have is we see kind of a high initial value for this current. It decays, this DC component decays exponentially, and then eventually we're left with just the symmetrical steady state current. But we're basically interested in what's the ratio of this asymmetrical term with respect to the symmetrical term. So it decays pretty fast, but it does put stress on the breaker during the first cycle. And it's going to be dependent on the type of system we have. If it's a highly reactive system, X to R ratio is high, that's going to have an impact, as well as when the point in wave in which the fault occurs. And if we have typical X to R ratios which are high, then typically worst case is going to be when theta is equal to 0, that we're kind of at a 0 crossing as far as the source voltage is concerned. So for this scenario where I have this particular X to R ratio of 10, which would be kind of a typical value for transmission, this shows what we're going to have for this this ratio. In this case, we're going to have 1.74. If this X to R ratio drops down to say like 5, you can see that this asymmetric to symmetrical current difference is going to drop down. And finally, if we have X to R equal to 1, you know, it drops down even further. So the more reactance we have with respect to the resistance, the higher ratio we're going to have, the worse this asymmetrical current could actually get as far as circuit breaker ratings. So just kind of keep in mind that typically for transmission we're going to be up around here. For distribution it's going to be a lower value, maybe a factor of 3 or so. As far as what's the worst case, well, the worst case would be as the X to R ratio gets larger and larger and larger, where basically you could think about this maybe going to infinity. We hardly have any resistance at all. And if you were going to go through the analysis on this and like plug this into MATLAB, what you're going to see is this worst case ratio is going to tend toward 2. All right. So another takeaway in this case would be, well, how bad could this get? Well, basically, this could get as bad as we get a current doubling, where the asymmetrical current could be a factor of 2 times greater than the symmetrical current. Or in other words, another way to think about this, if you were going to do just a normal steady state phasor calculation, you'd have to multiply that by 2 to actually get what could conceivably be the worst case peak current that you would actually see in the field. All right, so I'm going to go ahead and in another video, and I'm going to go through a worked example. And this worked example is for a 34.5 kV system. You'll see a lot of the examples I do in class, I would use common voltage levels. So 34.5 is a very common voltage level for distribution. We're working this at 60 Hertz. And I'm giving you the Thevenin equivalent impedance in this case in ohms, so 1 plus J3 ohms. So it's not a really high X to R ratio. But sometimes what I'll do in some of these problems is I'll give you maybe like a per unit reactance, and you'll have to convert that actually inductance. But for this particular problem, what I'm going to do is I'm going to go ahead and work this in a separate video and basically show you how you can actually go through the steps of actually calculating what the current's going to be. And the other thing we're going to do to make this a little bit more complicated is, instead of assuming that the fault occurs at theta equals 0, I basically know the voltage instantaneous value when the fault occurs, so I want to take that into account in my example as well. And so this will be in a separate video, this particular set of numbers for this case. Another thing I just wanted to mention before I finish this particular portion of the lecture off the PowerPoint slides is I've got another video on creating this particular circuit in PSCAD. And so this is kind of assuming that you guys already have PSCAD, the student version, PSCAD freeloaded on your laptop, or you're using VCL. So anyway, what you would do, this just kind of shows a sequence of steps which are also in the video, but basically what you need to do is you need to create a new project. So in the PSCAD lexicon, you would have like your workspace where all the different projects are available would be in this workspace directory. And then what you could do is you can add a new project. In this case, this is going to be called our example. I'm going to go ahead and give you the PSCAD file that you can actually load this directly in instead of having to create it from scratch, but I think it would be a good exercise for you to create this from zero. So what you do is you basically have to kind of drag and drop all the different elements on the screen, as far as having a source and the resistance and inductance for the line. You have a breaker, you have ground, you have a place where you're taking a measurement at. And so this is kind of gone through in the video. Just keep in mind these are the values that you need to load in. And then what you do is you wire the components together. And so there's a control W you can use to go into the wiring mode to make all the different connections. And one thing you have to watch out for when you're doing this is sometimes you make a wiring, you think you're making a wiring connection, it doesn't take. And so if you get an error, that just means you didn't quite get the components connected together right. And then you have to go ahead and you have to create what we call these channels. The channels is basically the mechanism we use to go between measurements in your circuit drawing and plots. All right, so you have to make this linkage to what we call these channels. Something else you need to do too, if you have a switch in here, you would have to have some logic that's driving that switch. And so you would have to set up what we call time circuit breaker logic, which we also go into the video. that basically ties to this circuit breaker model. And then the final thing you would need to do is you'd need to insert a graph. So you would insert a graph pane, and then what you could do is you can drag and drop one or more of these channels onto the graph, and then that's actually what you would need to do in order to create plots. And then finally you can excuse me, finally you can run your case. If you hit the run icon, you can go ahead and run your case in this case. I think in the case of my example, I was running this at a resolution of 100 microseconds. Obviously, the smaller the time step, the longer it'll take to run, but you get more accuracy that way. So anyway, what you'll see as a result of this particular PSCAD case is you'll see you're going to get something that matches what you got when you work this thing through by hand. And that's kind of what I do a lot in this class, is I'll have you guys do a homework, and I'll have you do it by hand first, and I'll have you guys verify the solution by running the PSCAD analysis. And that way you start to get some confidence as well that you're running PSCAD properly. Finally, as far as some references, I do have some written notes. What I was trying to do in these written notes a while ago when I put these together is basically kind of redo some of the explanations in the Greenwood text. And so these are kind of like targeted explanations of some of these different use cases. There's also, if you want to go back to the original Greenwood book, this is actually in section 3.2. And there's another reference I have too on switching an RL circuit, which is also available as an ebook in the library as well. And then finally, what I'd encourage you to do is go ahead and download some of the PSCAD manuals. Basically, you have like a set of instructions for downloading PSCAD free, so you can use that to get this set up on your laptop. There's also a pretty decent video they have on creating a simple circuit. My video is just for an RL circuit, but they have a little bit more of a general circuit, so it might help to go through this video first before doing your homework. They have a user's guide. This is more about the user interface, so it's like setting up the circuit and dragging and dropping the model elements and making plots and stuff like that. But then as far as under the hood, how PSCAD works, there's a model theory document which gets into the theory behind the models, how they actually do the math behind the models. And then finally, there's a knowledge base section where it has a lot of different examples. And so let's suppose you wanted to know, like, how do I set up PSCAD to do like a wind turbine generator? Well, they've actually got cases in this knowledge base you can actually load in, see how they set it up, then you can make modifications of that for the particular application that you're interested in. So that's also a pretty good resource where they would have a number of posted examples. Their technical support's also pretty good. If you send a note to their technical support, a lot of times they may send you some additional cases that aren't loaded up on their website already. So let's go ahead and close this video out, and then what I'll do is I'll work through an example by hand then.